We will dive into the material for today, which is going to be the bridge between the two topics that you see on the screen here. So we're going to be looking at the independence of vectors and systems of linear equations. And then we're going to start, I think, if we have time, and I think we will, to look at how we actually solve linear systems in a more efficient way. And some of you may have seen this before. That's where we're going to head to some of the clicker questions. But for many of you, it'll be a new way to manipulate equations that'll be a little faster. So with that in mind, let's dive down to this kind of analysis that we did here. So when we were looking at systems of linear equations, we framed them in this way here, where we had vectors as our building blocks. And these, if we're thinking about linear systems of equations, these were column vectors, going back a couple slides here. If we had these unknowns, these multipliers of an unknown coefficient, if we had these constant multipliers of an unknown coefficient, and we're trying to find the coefficients that make this equation true, then we ended up with vectors and then multipliers, scalar multipliers. And this is going back to, why do we think vector spaces are important? Well, because we're now allowed to safely combine these vectors with scalar multipliers, add them together, do all the vector space stuff that we've been doing, and know that things aren't going to break along the way. The questions are well defined. So the recasting of this kind of equation, which is what you've grown to know and love, into this form here is nothing dramatic. We just literally take the coefficients and put them into vectors here. And that changes the system of linear equations into a single equation with coefficients and vectors and whether they equal the vector that ends up on the right-hand side here. And what we saw was there's exactly three cases that can come out of trying to solve these equations. We can have our set of vectors that can't reach the right-hand side vector. So it has the two sets of vectors, the left-hand side and the singleton W on the right-hand side here. And if it turns out that with the, again, I think of building block vectors here as sort of a mobility thing. So imagine yourself, you're at a point, you're at the origin, and you're trying to move, kind of like on a chessboard. Well, you can only move in the directions of the vectors you've been given. You can only move in the directions of V1 through VP. And if it just turns out that you can't get to W using those chess moves, scaling and adding them, then there's no solution to the system of equations because we can't make W out of linear combinations of the vectors we've been given. And that's fine, that's an outcome. A second outcome is where we do get a W we can reach with our building blocks. And so an extra condition, that set of vectors is linearly independent, then we're going to have exactly one solution to our set of equations. There's going to be a unique answer, a unique set of x's that make this work. And then to contrast that, if we have linearly dependent vectors here, well, because we can kind of remix these things in themselves to get a zero vector, we can do this thing that we work through with cycles. We can get to W and then we can do sort of silly cycles outside of that if we want to, and get back to W over and over again in different ways. That led to an infinite number of solutions in that case. So you'll need to memorize those three cases and those three conditions. And we're just going to see this play out through different contexts when we're looking at different systems of linear equations as we go forward. However, because this is an official proof-based math course, we can't just have those statements of, it kind of looks like those three outcomes are the reality. I mean, these are nice statements, but we have not proven them yet. This is just sort of a hypothesis based on some examples. So we are now going to go through those three examples here, and we are going to prove them. And I apologize, I always keep forgetting to turn on the automatic subtitling there. All right, so we are literally going to go through these three things, and we're going to prove each one of them one after the other. So we're going to do the easy one first, which is prove that if W is not in the span of our vectors, then there is no solution. Okay. Well, this is by definition, because the span of V1 to VP is the set of all vectors of the form let's use our x1, v1, all the way out to xp, vp. Let's call this v, where the xi's are some numbers in the reals. So what is the span? It's linear combinations of vectors, of the vectors I have to build with. And linear combination just means some coefficients out front that are real, and I can pick any real numbers I like. Any real numbers as these multipliers works fine. Well, then we said W, if W is not in the span, but W is not in the span of V1 to VP, which means there does not exist xi's, elements of the reals that satisfy. And this time I'm going to highlight the difference. Here's my W equals x1 to v1 to xp to vp plus that. So again, it's often hard to see these with equations. That's why you need all the words around this. So this is not like calculus. We can't find coefficients that make this work. And so that means there is no solution to the system of equations because we have no x's that actually work for this. There are no x's, xi's that satisfy, when we think of it as an equation, the equation x1 v1 plus xp vp equals w. Now that one feels very circular, I admit, but it's really just translating the words about span and starting off not being in the span. Then there's no solutions if we look at this as a system of equations. All right. It gets a little more interesting for the next two, because here we're trying to contrast, okay, there is a solution in both cases, if it's independent set of vectors or not, dependent. And then we're putting the extra layer of, well, how many solutions are there? So we've done something like this before when we said, like, there's exactly, let me do a similar comparison here, similar to only one zero vector in a vector space. This was back in week 2. So there are themes that come back in terms of how we structure our proofs. Sorry, just going back one. Would you have to prove that this statement is that there is no solution because there does not exist xi's that satisfy this equation? So it's not this line here, it's this collection here of those 3 lines. There exists no x's that make this true. What's another way of saying exactly that? Then there are no x's that satisfy this equation. So it's just translating those 2 equivalent statements, one in the context of equations, one in terms of span, really. Hope that made sense. All right, so yeah, so if you look back at those proofs, you'll see that there was a structure that we used, which was in the vein of the contradiction proofs we saw before. So what we're going to do is assume, well, we're trying to prove there's one. We're going to use that to prove there's a logical contradiction. And so we're going to assume the opposite of that. And in fact, we're going to assume that there are 2 solutions to the equation. And so again, the reason we're assuming that there are 2 solutions is because we're going to say if that's the case, there's 2, we do some work and we show, well, actually, those 2 end up being identical to each other. All right. So what would 2 solutions look like? Well, let's build this out here. So let's not use x's anymore. So let's say, for example, that alpha 1 v1 plus alpha 2 v2 plus all the way out to alpha p VP is equal to W. And that our beta, because beta is our next letter up here, and sorry, just one sec here. If we have a second solution, beta 1 V1 plus beta 2 V2 plus beta P VP equals W are both solutions. Okay. So what does that mean? There's some coefficient for V1, V2, and VP that adds up to W. And there's some other set of coefficients that also adds up to W. That's what we mean by two separate solutions. I can find this collection of values, X's here now alphas, and this other collection of X's, well, call them here betas for a second. And what I want to do is show that those alphas and betas end up being the same. And that gives us a little bit of a hint because we are going to take advantage of the fact that the vectors are linearly independent. If I take a look at this left-hand side for both of these and think, wait, linear independence, what does that mean? What does that mean? It means when I try to add up these vectors and have it equal 0, then special things happen. I don't have a right-hand side here of 0, but I can get one if I take this whole equation, or take the left-hand side, and let's call this a 1, and minus the right-hand side, sorry, minus the left-hand side of 1 minus the left-hand side of 1. Oh, jeez. I apologize. Left-hand side of 2 would be a more reasonable thing to do here, 1 and 2. There we go. So we've got the two equations. We're going to do what you usually do with equations, which is take one of them and subtract the other. And why is this okay? No, we haven't done a lot of these subtracting and adding equations. Well, because now this is a set of vectors. This is a vector here. It's broken down into sums of vectors, but this is then subtracting off some other vectors. We're allowed to do that because we're closed under addition and closed under scalar multiplication. And when we do that, when we use associativity, we're going to have alpha V1 minus beta 1 V1, and that's going to give us a common coefficient of alpha 1 minus beta 1 V1. If I just go down the stack, both of these are vectors and both of these are scalars. So I'm going to get this difference between the scalars here when I do my subtraction. And then I'm going to get, after that, the alpha 2 minus beta 2 times V2. And you can see where this is going, all the way out to alpha P minus beta P and times VP. Now the fun part is the right-hand side. So we can take the right-hand side of equation 1 and subtract the right-hand side of equation 2, because that's just a vector minus another vector. Well, guess what that vector is when I take W minus W? That is the 0 vector for my space. Okay, now that sounds very handy because we now have an equation that ties right back to our statement about the vectors being linearly independent. When we have a right-hand side of 0 and we have a linear combination here, so let's do this way, linear combination of V1 to VP, V1 to VP, and a right-hand side equal to 0 vector. There is exactly one solution to this. And here solution means set of coefficients that make this true. And that's exactly 0 for all those coefficients. Because the set V1 to VP is linearly independent. What does that mean about our coefficients? It means that these coefficients, when the right-hand side equals 0, have to all equal 0. It's the only choice if linear independence is true for the set of vectors. All our alpha i's minus beta I coefficients must be 0. That's exactly what it means to be a set that is linearly independent. There's no wiggle room. The only way to get them to go back into a loop, to go back to the start, is to have all the coefficients 0. Well, that means, as a nice consequence, that if those alpha i's minus beta i's equal 0, then all the alpha i's equal beta I. Oh, well, if that's the case, let's just take a look back up here. What was the difference between these alphas and the betas? Well, they're the coefficients for the different vectors. We said these were different solutions, but what we just showed it actually in the end is it's the same solution every time. These values for alpha 1, beta 1, alpha 2, beta 2, all the way up to here, it means that our two solutions are in fact identical, or they are the same solution. So even if someone came along and said, "Oh no, I've got a brainwave. I solved this in a different way. Here's my second answer." You know, you found one answer your way, and then someone comes along and says, "Oh no, I got a better answer. It's this one here. It's these 10 numbers, whatever the betas are." You can just go through this proof and say, "All right, well, I can take my answer and your answer. I'm going to subtract them. That's going to give me an equation where I've got 0 on the right-hand side. And then the coefficients here all have to be 0 because it's a linear independent set. And so my answer that I found, the alphas, and your betas that you came up with, they have to be the same. There's no other possibility. If we came up with two solutions, the actual coefficients, the actual values that we get in the solution end up being the same. So therefore, the solution alpha i's must be unique. All right, now seeing some chat things come up there. Let me just flip on that. I just wanted to get that final push there together. Does the question tell us it's linearly independent? Absolutely. Remember, this is case 2. We had 3 cases we were looking at, not in the span at all, the right-hand side not in the span at all. Then the other 2 cases are the right-hand side is in the span, but we have linearly independent vectors. That's this one. And then on the next page, not surprisingly, we're going to look at the opposite case where we have linearly dependent. So this one is conditional on linear independence. Absolutely. I'm not quite sure, Darius, you're missing the vectors, which is, I think, so each of these things, remember, is multiplied by a vector. All I can see in yours is coefficients. So that might be the pretty much involves taking a shortcut when you're writing it out. But remember, these are vectors, and when I add these two things together, it's like adding 5 times a vector plus 6 times a vector. I get 11 times the vector. So we're just using that kind of associativity and distributivity of scalar multipliers. So this is a vector, W is a vector, and W is a vector. So when we subtract, this is really the definition of, or one definition of the 0 vector. If I take W and I subtract its additive inverse, if I take W and add its additive inverse, or I subtract W, same thing, then I get the 0 vector on the right-hand side. Again, all these are vectors too by the time we're done. So it's vectors all the way across here, scalar times a vector, scalar times a vector, scalar times a vector. And yes, this is absolutely the, okay. This is one solution case. This is the one solution case, absolutely. So going up to the top here, we have a set of vectors. They're linearly independent, and we're trying to show that that leads inevitably to there being only one solution to the equation here. Add up combinations of the vectors to get some target vector W, the right-hand side vector. Oh, if alpha and beta were additive inverses, that wouldn't help actually, because you get a double negative. You get alpha plus beta. Yeah, you end up with alpha plus beta. That's not what we're doing. We're taking this equation and subtracting it, which is the same as adding beta's negative inverse, if you want. I appreciate the thought, thinking of all the studying you're doing, but that's overcomplicating a little bit now, because we know that minus a number is the same as plus its additive inverse, plus its negative version. So those actually end up being the same in vector spaces. Sorry, with coefficients have to equal. Different logic. Sorry, Avery, I'm not quite sure if I got into your question, so I'm going to pause on that one. One last one here from Darius. So the left-hand side from my right-hand side was 0. You've got the conditionality backwards. If I take two solutions, I can always do this. So we could do this on the next page with our linear dependent set. I can take one solution and I could subtract another solution equation, and I would get this every single time. And it would equal 0 on the right-hand side, just because the right-hand side is W on one and W on the other. You subtract them, you get 0. The solution being unique comes from after that. Okay, now I'm looking at this equation and going, oh, this is something I've seen before. A right-hand side of 0 is something special about linear independence, and I've been told that this set is linearly independent. So I can go from this line, which would be true no matter what my sets were, to this next statement here. The coefficients must be 0 comes from linear independence. If they weren't linearly independent, I could not say this. Everything up here would be true still, but my coefficients being 0 comes from linear independence. So, all right. Okay, I appreciate the questions on this, because this is very new, especially with the proof structures and things like that. Let me give the third example here just to compare and contrast, and then we can do a more thorough follow-up if that is needed. All right. Okay, so because we're actually going to see the same kind of little different process here. Here, we're going to be working on case 3. So here we have a linearly dependent set of vectors. So again, these are vectors that somehow can kind of add it up together, scaled, get back to 0. And the consequence of that is that there's going to be infinitely many solutions to this. So taking a look at my own notes here so I don't butcher this too badly. All right. So here, for this case, we're going to go a different direction. We'll start with one solution. Oh my goodness. We're going to start with legible handwriting. We will start with one solution, one solution. And then show it can be a foundation. It can be a foundation for building an infinite number more. All right, so we're gonna have one solution to building block because there's, okay, we know it's W's in the span, so there is a solution. That's our first line here. W's in the span, so there has to be one solution to this equation. And then we're going to say, okay, so if that's true and the set's linearly dependent, what can we extrapolate that to? So let's let, alpha 1 to alpha p be a solution, which means that alpha 1 v1 plus all the way out to alpha p vp equals w. And a little side note, we know this exists. We know at least one solution exists. At least one solution exists because W is an element of the span of V1 to VP. If W is in the span, then that means I can add up some set of coefficients for the V's and get W. That's what it means to be in the span, is there's a way to linearly combine the vectors to get W. All right. Okay. Now, let's add some other things, though. So now we're going to use our linear dependence. Now, because the set V1 to VP is linearly dependent, then there exists beta 1 to beta p such that, so that ST just means such that, what do we say? All right, so for linearly dependent, it's almost the same equation form. It's almost the same equation form as this, except for dependence and independence, it's a right-hand side of 0. So I'm going to put it here in a different color just to contrast. B1, V1, plus all the way out to beta P, VP equals the 0 vector. And again, some of this is with at least one beta I not equal to 0. Okay. Let me rewrite my beta there. So let me just pause here for a second to absorb the beauty that is this. So we know there's a solution. If I add up some combination, one particular combination of my vectors, I get W. Now, oh yeah, by the way, there's this totally separate thing of if I add up my vectors in a different way, I get the 0 vector because they're linearly dependent. And by adding them up, I mean there's some meaningful non-zero collection of them that when I add them and scale them, I get back to 0. Okay. I don't think there is a fancy thing for such that. It's always been ST. There exists and for all, but not, yeah. The backwards E is there exists. This guy would have a fancy symbol. The vertical line means so many things. That's not my first thought. I just use the short form, ST. Anyway, right. So some collection of these vectors adds up to W. A different collection of these vectors adds up to 0. But then what happens if I add those two equations? Thinking where we're going here, I can get to 0. Sorry, I can get to W. I can get to W. If I add 0 to that, I'm staying at W because that's one of the properties of our 0 vectors. When I add it, nothing changes. So if I add these, let's give them numbers. Same kind of thing we did last time. Add 1 and 2. Add 1 plus 2 this time. We get alpha 1 plus beta 1, V1. So total here, plus all the way up to the end, alpha P plus beta P, VP equals, well, the right-hand side again is just our W vector plus the 0 vector, but we know what that is. That's just W again. Oh. Well, that means we have a new solution. That means alpha 1 plus beta 1 all the way out to alpha P plus beta P is also a solution. Why? Because look at it. If I add up those multipliers times all the vectors, I get W. That's what it means to be a solution. I satisfied my equation. And at least one of those betas is not 0, right? That's what we set up here. These betas aren't all 0 because I've got a linearly dependent set. There's some of them that is not 0. And so that means, unlike last time where we kind of had two solutions, but they ended up being the same under the hood, this means the solutions alpha 1 to alpha P and alpha 1 plus beta 1 all the way out to alpha P plus beta P are different. They have some fundamental difference in them because I've added something non-zero to it. So we have two solutions. Okay, well, 2 is not infinity. There's a bit of a gap there, but let me just pause there. Going back to the questions before we do the infinity part. So going in order, so span. If you have, what does it mean? I'm feeling we're just talking circles. Okay, take a step back. What is the span of a set of vectors? So we have a set of vectors, here it is. The span of a set of vectors is literally the things that fit what I just boxed in red there. Any multiplier of V1 plus any multiplier of V2, I'm allowed to do any linear combination like that to make new vectors. And all the things I can make out of those new vectors is the span. So if we say W is in the span, that means there are specific coefficients that will add up and give me W. That's sort of the span means all linear combinations. If W is in the span, it means it's just one of those linear combinations, that there are the number 2, the number 5.7, the number 12 here, when I add them up times my vectors, I'm going to get the vector W. That's what it means to be in the span. So that's one thing that was off on the side. We're talking about systems of equations. And the second question was, what about this non-zero dependent part? So this is a totally separate part here. Sorry, here. All right. Because the vectors are linearly dependent by themselves, now we're going to go off on the side and say, oh, that's great. I don't care about the equation for a second. I'm just going to think about these vectors. These vectors are linearly dependent. So when I write out, this is the kind of thing you have to memorize, right? There's the definite. What does it mean to be linearly dependent? Well, it means when I write out this special equation that involves the vectors equaling or adding up to the zero vector, that was how we started defining dependence versus independent vector sets. Then when I write out that equation and it's a linearly dependent set, then there's going to be some non-zero beta in there that's going to make this work. That's going to satisfy this equation here. That's literally the definition of linear dependence. So as you're writing up your study sheet, getting ready for the midterm, this should be like side by side. Linear dependence means this equation with the words, there are some non-zero solutions. Linearly independent means same equation, but only all zero coefficients satisfies it. So we're literally translating this into its definition. There's some beta that's not, there's some beta in a set that's not zero. That's what makes a set of vectors linearly dependent. There's this equation and this statement together. All right, so oh yeah, so this would be not true. So sorry, full question. If this was a linearly independent set, we would get to this stage here, except our conclusion is that every single one of these betas has to be what? If it's linearly independent, the last case, every single one of those betas has to be zero. So we would get to here and we'd be like, oh, I have two solutions. I have all the alphas, and then I have all the alphas plus betas, but every single one of those betas has to be zero. So I've added zero to everything, even though it looks different because I put symbols there. The fact, if we were in the last case, do not think about this for this case. If we're in the last case with linear independence, all of these betas would just be zero. And so I could cancel them out and I would be back to my first solution. So that would be the difference between the two scenarios if we walk through them here. And why did, oh yeah, so why did these, because I had two equations here. Why would alpha plus beta equal to because we had two things that were true. We had this equation. Hey, my alphas times the vectors equals W when I add them up. And over here, I had the betas plus the vectors adds up to zero. And so I just added those two equations. If I have V1 times alpha plus V1 times beta 1, oh, well, that's this term here. Same all the way down the line. If I take VP times alpha P and VP times beta P and I add those, I'm going to get VP. And so when I add the right-hand side, though, the key thing is I'm adding W to 0. Oh, wait, W plus 0, that's W again. So that's what gives us the same right-hand side, because we added 0 on the right-hand side, but different coefficients on the left. All right. Could we have subtracted the equations? Absolutely, because you would have subtracted 0. In fact, that's actually, you could get a totally new set of answers there if you wanted. So you could subtract the equations and get alpha 1 minus beta 1, alpha P minus beta 3, beta P, and that would give you a third solution. But I'm going to take a shortcut and give us an infinite number of solutions with one little trick. All right. So pause here. This is two solutions. I want an infinite number of solutions. So what I'm going to do is go back to this equation here. Yeah, this equation here. And move this 2 over just a hair. And notice what I can do with that, because this one has a right-hand side of 0. I can't do what I'm about to do with this equation here, because it has a non-zero right-hand side. But I can put a multiplier in here. Some k that's real. I can multiply by 0. And it's not going to change anything, right? That's one of the properties, again, of vector spaces, is that any constant, any scalar times your 0 vector is still a 0 vector. Well, that means I can do the same thing to both sides, right? No. So change nothing here. This is still true. Because these vectors are linearly dependent, there's betas that make this work, but I can also scale them all by that k. And then when I add this, I'm going to have k times b1. So I'm just going to slide a little k in here. K times b1. K times b2, beta 2. And k times beta p. Doesn't affect the alphas because the alphas were up here. They're in the separate equation. But if I put a k in here, nothing has changed. In fact, so what I just get down here, I'm just going to tweak this a little bit. You might have enough room to slide it in. K beta 1 and k beta p. Oh, so alpha 1 plus, say my betas have been 1, 2, and 3. I could use 2, 4, and 6. I could use 3, 6, and 9 for my betas. I can use I could use 1.5, 3, 4.5. I can use any multiple of those betas. And because it didn't change this equation, it didn't change the fact that when I added W to 0, I stayed at W because I just am taking 0 again, just in different multiples of it. And so we actually get all these solutions for any k, any real k. And that means there are an infinite number of solutions. Each k gives a new solution. And because k can be any real, well, I can pick an infinite number of real k's. That means I'm going to get an infinite number of solutions back out of this. All right, let me pause there because that's sort of a smaller step, but it's a bigger step because it messed kind of the calculations up. Let me pause there for follow-up questions on that. Feeling okay about that? Not seeing an explosion in the chat. Okay. All right. So what did we just do? We just found one of the fundamental relationships in linear algebra. So going back, we had these 3 statements that I made here. If we look at a set of equations that involve vectors, so it's an equation equaling a right-hand side vector. And I appreciate, especially as you study this, it's easy to get confused between, was there a vector in this one or was it a 0 on the right-hand side? Do whatever you need to do here. But when we solve equations, the right-hand side can in principle be anything. So if we keep this open, the zeros come in with a linear dependence and independence only. So we've got a vector equation with a right-hand side as a vector. One case, W is not in the span. And that just means I literally cannot combine these building blocks to get to W. If that's the case, then there's no answer. There's just no solution. Then there's the 2 cases where, okay, there is an answer. What distinguishes, or what's one way to distinguish how many solutions there are? It turns out it doesn't matter. Dimension doesn't matter directly. Number of equations doesn't matter directly. Is the set of vectors you're playing with linearly independent? Then there's going to be one answer. If that set of vectors is linearly dependent, then there's an infinite number of answers. Done. That's it. So looking forward to your web work for this week. Yeah, okay. Basically summary of what I said here. One of your web work problems looks sort of like this, where they give you a collection of 2 variable systems and ask you to sort of translate what we just did here into vectors terminology, and specifically determining the number of solutions, which is either 0, exactly 1, or an infinite number. Now, I should state, you could have answered this question before because you've solved systems of linear equations, and 2 by 2 is a walk in the park. What we're asking you to do here is practice the new skill of looking at this, translating into vectors and going, oh, maybe this is why. So what does this look like, especially for 2 by 2? 2 by 2 is simple enough that you can start to see patterns that are also true in the bigger ones, but they're harder to see when you get to 3 by 3 and 4 by 4, that kind of thing. So this is the same as the vector equation 1, 2, and 5, 10. This is our V1, that's our V2, that's our W. So if you want the translations, this would be alpha 1 if you wanted, and alpha 2. This and this are exactly the same set of equations. I'm looking for the X and the Y, I'm looking for the alpha 1, the alpha 2. Doesn't matter. It's exactly the same thing. You can actually write it out by component, right? X times 1 plus y times 1 equals 5. 1x plus 1y equals 5. 1x plus 2y equals 10. 1x plus 2y equals, that's the same thing. Right away, because we can, remember this little side fact, I should put this here. For sets of 2 vectors, we have this nice simple case that linear dependence is the same as, or is equivalent to, scalar multiples. Or if you like, if we are dealing with vectors in real space here, parallel vectors. I cannot emphasize this part here enough. If you have 3 vectors, life is complicated. You have 4 vectors, life is complicated. 2 vectors is the only sweet spot where you're like, oh, linear dependence and dependence is easy to check. So do not read too much into this, except we're working in 2D here, so life is nicer. So here we have 1, 1 and 1, 2 is linearly, we take a look at these vectors. Well, these are clearly not parallel. So they are linearly independent. And we'll have some other shenanigans later on that'll prove what we're going to do here. But if you imagine these 2 vectors drawn on the plane, we have the 1, 1 vector, we have the 1, 2 vector, and we have the vector 5, 10 out here somewhere, 5, 10 out here, whatever. Because these 2 vectors are linearly independent, there's some combination of them. In fact, there's pretty easy combinations. Five of these guys will get you to the right-hand side, the 5, 10 here. Is there any other possibility? Is there any other way to get to that point? No, because we have this condition here that exactly one solution comes out of linearly independent vector sets that we're working with here. Exactly one solution. So there is a solution. I should put that in the side here. This is in the span of, let's call it V1, V2 for brevity here. So there is a solution, but because these vectors are linearly independent, we're going down this stack here of exactly 1. Just going back, if you need to have this page in front of you, we just broke down into this case here. W was in the span of my vectors, and that set of vectors was linearly independent, so we have exactly 1 solution. That's the 2 pieces of ifs leading us to a then. All righty. And we can kind of rinse and repeat that. Here we have x times 2, 4 plus y times 3, 6 equals 1, 1. And here we can tell that this set of 2, 4 and 3, 6, these are multiples of each other, clearly. If I multiply this by 1.5, I get the other one, is linearly dependent. And so going back up to here, what are my options? Well, linear dependent, I could have an infinite number of solutions or no solution. It's going to be one of those 2 cases there. What is the determiner? It's the right-hand side being in the span, yes or no, of these vectors here. And you can solve it, you can set up equations, or you can draw it if it's a nice simple enough case like this. So here, if we draw the 2, 4 vector, that's 2, 4. And if we draw the 3, 6 vector, 3, 6, and then we take our W, which is 1, 1, it's on the 45-degree line. That's our W, 1, 1. By following multiples of this vector, we're never going to get to this vector. We can never get to that point. So, but W is not, sorry, let's make it clear. 1, 1 is not in the span of 2, 4 and 3, 6 combined. No matter how I play with those 2 vectors with linear combinations, there's no way to get to W. There's no way to get to that 1, 1 point. And so there's no solution. How many of these vectors does it take to make a W? Well, there's no way you can make a W out of them, so there's no solution. Sorry, the first one was linearly independent because it's easy to test for dependence. If they're multiples of each other, like these ones here are, if they're scalar multiples of each other, if they're parallel, then they're linearly dependent. So that's two vectors only. If you look at two vectors, they are either multiples, and so they're linearly dependent, or they're not multiples, and then they're the other thing. They're linearly independent for that. And so, yeah, in fact, here, the span check is actually the hardest thing. I mean, the theory is like lovely and great, but the span actually turns out to be the more problematic part of all of this. So let's just do the last one and see how it plays out. Notice the vectors are the same here. We have x times the vector 2, 4. Oh, actually, oh, no, that's plus. Okay. The vectors are a little different. You take the whole coefficient, 3 and negative 6 equals 5, 10. And because these are web work level problems, the intent here is to get you practicing thinking about these things rather than brute forcing through all the calculations. So a quick sketch of this scenario tells us that we have the vector 2, 4. That's our 2, 4 vector. We also have the vector minus 3, minus 6, which weight is a multiple of that. So these are multiples of each other. And then, hey, if we draw 5, 10, the point 5, 10 has that same 1:2 ratio. So 5, 10 is in that span. 5, 10 is in the span of 2, 4, negative 3, negative 6. That's our one feature. So right away, there is at least one solution. And then we also have the set 2, 4, negative 3, negative 6 is linearly, look for it. Are they multiples of each other? They are multiples. That means I could cancel them. I could build sums of them and scaling of them that I could go back to 0 with. That's linearly dependent. And these two factors together add up to there are an infinite number of solutions. Okay. In fact, is it worth even just building a couple? Yeah, just to illustrate this, if I just look at this equation and think it's all nice integers, if I made this out to 8, so 4, so if I took 4 of the first one, and then I added 1 of the next one, you can check this out. This is going to be 8 minus 3. Hey, 8 minus 3 is 5. And then it's 16 minus 6. That sounds not a lot like 10. But remember the logic that we used for the proof that multiple solutions exist here. If I can add 0 to this, then I can get another solution. And one way to get 0 is 3 of these guys and 2 of these. Sorry, 3 of these will give me 6 on top, and then 2 of these will give me minus 6. So I think if I add 3 of this and 2 to here, that'll give me 7, 2 and 4s, 3, negative 3, negative 6. This is our betas that we had before. This is our alpha 1, alpha 2, and this is our beta 1 and beta 2 that we had in the last proof. And if I take a careful look here, I'm going to get 14 minus 9. 14 minus 9 is 5. 28 minus 18. 28 minus 18 is exactly 10. Or we could do 10 of these plus 5 of these. It's going to equal 5, 10 again. And there's our infinite number of solutions, just with nice real numbers. Okay, let's pause there. That is actually close to the end of our time. I'll just tackle 2 questions that are there, and then I'll open the floor for other ones. Midterm, do we get any formula sheet? No. The actual list of formulas you need to know for this class is half a page at best, honestly. The proofs and sketches of the proofs, so you have those in mind, those are longer for sure. But the definitions and the things that go with them, like the definition of linear independence being an equation with properties, that is the kind of thing you have to internalize. Honestly, it's you can have a cheat sheet beside you while you're studying, but you've got to have it in your head as opposed to what was that definition again? No, it's got to be closer than that. So no formula sheet on the midterm is the long answer to that short question. Second one was, does a sketch count as proving it's in the span? This is a web work question, so I specifically solved it like I would a web work question where you're not asked to show all the work. So if it was something where it said, we would say this in the question, show that blah is in the span, or the general question might be, how many solutions does this have? In which case, finding out whether your right-hand side is in the span or not. If it's in 2 dimensions, I think you can make a compelling case. Like I put more words around this, like drawing the vectors here and here, gives this picture here. It is clear that 510 is a multiple of these as well. Anything beyond 2D, though, a sketch is going to be useless, and you'd have to do it algebraically. So I would say a sketch in 2D with words would be sufficient. It's a compelling argument. If it's in higher dimensions, you would have to do the span calculation separately. Oh yeah, how did I know? All right, so how did I know that adding 3 and 2 would do this? In my side calculation, remember what we had before? We had beta 1 v1 plus beta 2 v2 equals the 0 vector. So if I put in my specific vector here, which is 2, 4, and -3, -6, keep my right fractions, is the 0 vector. I just looked at this and said, well, how many, if I want to get 0, how many of these plus how many of these is going to give me 0? And then I thought, well, it's kind of mix and matching the coefficients, right? If I take 3 of these, because there's a 3 here, and I take 2 of these, because there's a 2 in this one, I'm going to get a 6 both ways. And one of them is going to be negative already because I already have a negative sign in here. So I know if I add 3 of these plus 2 of these, I'm actually adding nothing to the total. And so I could safely add 3 of these and 2 of these to the total and not change the overall sum. So that's how I got those in 3s and 2s. Basically mix and matching. There's a 2 here and a 3 here. If I put a opposite 3 and 2 with them, then they'll end up canceling out. All right. So that'll be the end of today's lecture. What I think we'll do on Friday is actually do a minimal amount of content. I'm going to take a look at the next week, and it'll be more likely be exam review, taking a look at old exam problems, things like that, for at least half of the class on Friday, and any new material on top of that. So no clicker. The next one was a clicker question. It was right here, clicker. So yeah, those proofs took a little longer than I anticipated. The joy of teaching this new format. So no clicker today. Definitely clicker on Friday though. So again, floor is now open for any other questions.